A very good day to the honorable adjudicators. My name is Ng Johan, and today I'm going to be presenting my poster titled Quantum Dot Lasers on Silicon, Enabling the Photonic Future. Let's start by defining silicon photonics as the science and technology of producing optical devices and circuits using silicon as the core material. Why does this matter? Because today's chips face two big bottlenecks. First, speed. Transistor counts keep rising, but clock speeds have stalled. Second, data. Modern AI and data centers burn massive energy, yet processors sit idle waiting for information to arrive. Next, why silicon? The reason is simple. We can leverage existing silicon infrastructure to develop and manufacture photonics easily. Integration on a chip brings three big wins: greater energy efficiency, higher capacity, and advanced compact functionality, just like transistors once did for electronics. Here is a simple scheme of a silicon photonic integrated circuit, and the on-chip light source has always presented the greatest challenge. Why? Because silicon is a terrible light emitter. Here's the physics. In direct bandgap materials, electrons and holes have the same crystal momentum and can recombine directly, emitting photons efficiently. However, silicon has an indirect bandgap. Electrons and holes have different crystal momentum, so recombination is indirect and requires a momentum shift. And because photon emissions alone cannot balance the momentum change, phonons are also released, meaning recombination usually produces heat instead of light. That's why today's state-of-the-art silicon photonic chips rely on external or hybrid lasers. But this adds cost, power loss, and limits scalability. Hence, the question here is, how can we grow efficient, reliable lasers directly on silicon? This is where quantum dot lasers come in. Quantum dots are semiconductor nanocrystals, often called artificial atoms, because their extremely small size traps electrons. Two important characteristics are discrete energy levels and symmetric gain spectra. Here, we can see that in bulk semiconductors, energies form continuous bands as electrons move freely throughout the entire crystal. However, in quantum dots, electrons are strongly confined in dots, so there are fewer alternative states, and this creates discrete energy levels that lead to some excellent lasing properties. Quantum dots also possess symmetric gain spectra, meaning that as energy is injected, the amplification of light wavelengths is centralized, leading to stable lasing. Now here's how a quantum dot laser works. First, a current is passed to inject electrons into the quantum dots. This current excites them to a higher energy state. As electrons return to lower energy states, they emit photons, and these photons bounce between reflective facets before escaping as a beam. The resultant beam is stable and coherent. Unlike conventional lasers, quantum dots can also be grown directly on silicon wafers through epitaxy. This not only simplifies manufacturing, but also improves heat dissipation, since the silicon substrate doubles as a heat sink. Here is a photo of an actual quantum dot laser, as well as a summary of the process of growing QDLs on silicon. For a very long time, QDLs have struggled with lifetime, but there is some exciting progress recently, and QDLs are starting to achieve longer lifetimes at high temperatures, which is important for many applications. The key advantages of QDLs compared to conventional lasers are: 1. Ultra-low line width enhancement factor, which translates to significantly reduced phase noise, resulting in a pure and stable light source. 2. Insensitivity to reflections. QDLs are not affected by reflected light. This eliminates the need for optical isolators. 3. Low threshold current, which translates to lower power consumption and energy-efficient lasing. And finally, defect tolerance, which allows reliable growth on substrates like silicon, where defects are common. Recent breakthroughs have solved the historic lifetime issue. Through advanced techniques, quantum dot lasers now demonstrate extrapolated lifetimes that meet commercial requirements. After 3 decades of development, QDLs are finally delivering on their promise. In the near term, they will form the backbone of sustainable, energy-efficient data infrastructure, but the real excitement lies further out. The ability to efficiently generate light directly on a silicon chip is more than a convenience. It is a critical enabler for future technologies, notably quantum computing. As such, quantum dot lasers on silicon are a force of the future, unlocking not only the power of light as a medium, but also a new paradigm of computing and information systems built beyond the limits of electronics. Lastly, here are my references. Thank you.